In this video, I'm going to be introducing the topic of describing distributions with numbers, specifically standard deviation and variance. So we've been talking about measures of spread, which are numbers that help us see how spread out a set of data values are. And so far what we've talked about is range, which tells us how wide the entire set of data is, minimum or to maximum. We've also talked about interquartile range, which we use for skewed distributions, and that talks about how wide is the middle half of the set of data. And now we're going to move into standard deviation, which is defined as the typical distance from the mean. This is what we're going to be using for symmetrical distributions. So let's start off by looking at an example. So we have 3 samples here of 7 cars traveling on a road, and that road has a posted speed limit of 25 miles per hour. And as you can see, in all of these examples, if you did the math, you would see that the mean and the median are all 25 for all 3 sets. The range is 40 because all of them go from a minimum of 5 to a maximum of 45. And all of these distributions are symmetrical. So none of this really gives us any information about how are those distributions different, although we can clearly, looking at them, see that they are very different. So we're going to use this to talk about standard deviation and how that measure would actually, in one number, describe for us the difference in these 3 sets of data. And that's important because how much each individual car speeds deviates from this mean of 25 is important information. It tells how much variability there is in that data set. You know, again, these are very small samples, so by looking at them we can get a general feel for what the variability is, but if we were talking about very large data sets, we wouldn't be able to visually just look at that and see. So again, the standard deviation definition is that it's a measure of the typical deviation from the mean for the values in a data set. Now that word typical isn't really a strong mathematical term, but that's what we're going to be using in this course. You know, it's just generally how far apart from the mean are all the values in the data set. And this is really important to understand because standard deviation is one of the most important statistical measures, and it's going to form the foundation for almost everything else we do in statistics going forward, at least in our introductory course. So it's very important to get a good, strong foundational understanding of what standard deviation actually is. So let's look at an example here. We have a graph here that shows the SAT critical reading scores for 5 students, and those data values are represented by the red dots on the line here. The mean of the data set is represented here by this star, and the deviations of 2 data points. They haven't calculated all of the deviations, but we're looking at the deviation of this highest value of 650 compared to the mean is a deviation of 102. That deviation, the difference, how far away is it? Versus this other deviation, which is negative 58, 490. The deviation is negative. That shows us it's below the mean, 58 spaces. So calculating the standard deviation would tell us how far all of the data values typically are from the mean, which gives us a measure of how spread out the data is. If we have a very small standard deviation, it means the data is going to be clustered closely together around the mean. And if we have a large standard deviation, it means it's going to be more spread out. Again, keep in mind that this is all related to symmetrical distributions. So we're using the mean as our measure of center, and the variability that we're looking at is figuring out how close or far away are our data values from the mean. So what's interesting here is, you know, this is somewhat interesting to know what the standard deviation is for this one particular set of data, but what we're going to be learning through the rest of the course is that standard deviation, the real power of that, is allowing us to compare multiple sets of data. If we had, for example, 2 schools and the SAT reading scores for those 2 schools, we would be able to compare the students at school A to students at school B. Standard deviation also becomes the foundation of a lot of the predictors. If we took a sample of 5 students, could we use that to predict the SAT scores of the entire population at a school? So standard deviation becomes very foundational from that perspective. Now, as we talk about standard deviation, as with everything in mathematics, whenever there's a long word for it, we abbreviate it with some sort of a symbol. So for standard deviation, this Greek letter sigma is used to represent the standard deviation of a population. So if we were looking at the entire school and we knew the standard deviation, sigma would be the character that we would use to represent that. You can type this on your computer by switching to symbol font and then typing a lowercase s, because as sigma is a lowercase s in Greek. If for some reason it comes up with this symbol that you're used to seeing for the sum of, that's actually a capital sigma, and it means you must have the auto caps on in some way. If we're looking though at the standard deviation of a sample, so in the previous example, those 5 people whose SAT scores that we have, then we just use the small English letter s to represent that. So there is a distinction there. We use the small letter s for a sample, the sigma for a population. And this is something you're going to see is fairly common in statistics, that the English character will be for the sample, the Greek character will be for the population. And as we learn more about statistics, we'll see it's an important distinction to make between those. So standard deviation is the single number most commonly used to describe variation, to describe the spread of the data. How close to or spread apart is it from the mean in a symmetrical distribution? And the way that we calculate it, it has this big fancy formula, and what you're going to be doing basically is figuring out how far apart every value is from the mean. So that's what this deviations from the mean is. We're going to figure out how far each one is from the mean and square that number. The reason we're squaring it is because some of the values will be below the mean and be negative, some will be above the mean and be positive. In a symmetrical distribution, if we just summed up all the deviations from the mean, the negatives and the positives, they're basically going to cancel each other out because it is symmetrical on both sides. So the way to counter that is to square every single deviation. Then we're going to add those all up and divide by the total number of data values minus 1. And for the purposes in this course, we're not going to worry too much about why we're taking the number of data values minus 1 as opposed to looking at it more like an average and just dividing by the number of data values. But once we've summed up all those deviations, divided it by the number of data values minus 1, then we're going to take the square root to sort of counteract that squaring that we did at the beginning. So in this course, you're not going to be required to calculate the standard deviation by hand. You can use Excel, and in our course site there is a video that shows you how to do that. But you will need to have a general understanding of how it's calculated, as we discuss on the next slide. Since standard deviation is the typical distance from the mean, calculating it involves basically doing what we just talked about. Finding the actual distance of each value from the mean, squaring that, adding them all up, and then dividing and taking the square root. So let's walk through an example of that. So to calculate the standard deviation of a set of numbers, the first thing we're going to do is compute the mean for the whole data set and subtract the mean from every value in the data set. Then we're going to take each one of those numbers and square them individually. Once we've squared them, we're going to add them all together. And then we're going to divide that sum by the total number of data values minus 1. So if we had 10 data values, we'll divide by 9. And then we're going to take the square root of that, again, to kind of counteract that squaring. So let's go through an example with 5 data points. These 5 data points have a mean of 10. So the easiest way to do this by hand is to set up a little table here. So we have our 5 data values in this first column. The second column, we're going to look at the deviation, the difference from the mean. So we're going to take the data value and subtract the mean, and we get these 5 differences here. You'll notice -8, -2, 1, 2, and 9. Now, you will notice here, if we had just added these up together, -8, -2, and -1, those all equal -11. Add 2 and 9, now you've got 0. So just adding those by themselves doesn't do us any good. So we're going to square them and come up with a sum of 154. So looking back at the formula and what we need to do next, we've done the top part of this fraction. We've summed the deviations from the mean. So the next step is we're going to divide by the total number of data values minus 1 and take the square root. So we're taking this 154, dividing by 5 minus 1, which is 4, take the square root, and that gives us a standard deviation of 6.2. What that means is these data values typically are within 6.2 of the mean, above or below. And we'll learn in the future that there's actually a way to predict things about the set of data based upon this. Most of the data actually will fall between 6.2 below and 6.2 above the mean. So now let's go back to that example we were looking at the very beginning. We have 3 samples of 7 cars, and if we calculated the standard deviation for those 3 sets, you would see the first set is 11.5, the second set's 13.2, and the third set is 20. Standard deviation, again, is a measure of spread, so we want to look at how variable are these samples. So looking at just the numbers within the samples, we would have expected that number 1 would have a lower standard deviation than something like number 3, because number 1, almost everybody went 25 miles per hour except for one person who went 5 and one person who went 45. So the speeds are very close together. Versus number 3, only one person went 25 and everybody else either went 5 or 45. So that's much more spread out. So that is represented in the fact that our sigma 1, the mean of that population, is 11.5, and our sigma 3 is 20. So we want to look at, what do the values of sigma predict? And again, it predicts variability. The greater variability in a sample of data is indicated by a larger value of standard deviation. Lesser variability has a smaller standard deviation. So, just as we've talked about with every other topic so far, what is the impact that outliers have on standard deviation? Because standard deviation is calculated using the mean of the data, we have to do the mean and look at the differences from the mean. And because the mean itself is greatly influenced by outliers, the standard deviation is also greatly influenced by outliers. In fact, it's actually influenced more than the mean, because we're using that mean to calculate it. So it's almost like propagating an error. If you make a mistake at one point, all your work becomes further and further away from the correct answer. The same thing is kind of true here. Because the mean is impacted by the outliers, anything calculated based on the mean will also be impacted. And as with the mean, the outlier would pull the standard deviation. So if the outlier is on the high end, it's going to influence the standard deviation in that direction. So now I just want to address another term that you'll see discussed in conjunction with standard deviation, and that is variance. And what I first want to do is make a distinction between variance and variability, because those two words do seem very similar, but they're actually very distinctly different in statistics. In statistics, words have very specific meanings. Variance is a specific statistical measurement that is equal to the square of the standard deviation. So it is a measure of variability, which is just a general term that we use to describe a data distribution. So variance is a very specific measurement. It has a formula to calculate it. It is a specific number, as opposed to variability is just very much a more general term. Variability, the data is more spread out, the data is more clustered together. So it's important to see that distinction there. Now, the reason that we would use standard deviation, if you notice from the definition of variance, variance is the square of standard deviation. So you may say to yourself, why don't we just use variance rather than doing that last step in square rooting? Because now we're square rooting and then squaring again to get the variance. The reason that we use standard deviation instead of variance is because taking that square root makes the standard deviation look more like our data values. What I mean by that, it's easiest to explain by kind of giving an example. So for example, if we have a set of data that spreads from 0 to 100, the standard deviation of that set of data is, could be 20, which means that most of the values fall within 20 of the mean. So say the mean was right at 50, it would mean that most of the data values fell between 30 and 70. However, the variance of that data set, which is the square of the standard deviation, is 400. 400 is not really a number related to that 0 to 100 spread, so that makes it a little less easy to compare to the exact set of data. So standard deviation is really the term that we're going to use, but it's just important that you have a general understanding of how that relates to variance and what variance is in case you see that term again in the future. So that kind of finishes off our presentation for today, and we'll see you next time.